So pigeonhole principle sounds like, how does this connect to number theory? Thank you. But this is really all about remainders again. And the reason it is where it is in the book is because, let's say you have 9 locations that you could put birds, pigeonholes they call them, and you have 10 pigeons. You can put them, any array that you want, but you are absolutely certain that in one of these boxes there's going to be 2. And the way that you know that is if you distribute evenly. The one thing I like to say, distribute systematically, analytically, evenly, however you want to say it. Then what happens is 1, 2, 3, 4, 5, 6, 7, 8, 9. That 10th one has to go where one of the other 9 birds are. And that's what they mean by pigeonhole. And the pigeonhole principle is, if you take n items, and divide by m, they're calling it pigeonholes or just locales. Okay. You're going to get n over m as the least available total. So in this case, if you get 1.083, which we're going to see in a little bit, each one of these is going to get 1 in it, but then this remainder means that one of them is going to have a duplicate. And so that's what they're talking about with the, or 2 or whatever we have for an integer here. So this is the evenly part, distributed. And then this is going to be the extra. And you know that it's going to be, in this case, 1 plus 1. So at least one pigeonhole will contain more than 1. That's what that means. And then at least one pigeonhole will contain at least n over m when we look at the greatest of those. There's a proof here that's real analytical. They're using some, I think it's contradiction here. I'll let you read that. That proof isn't super helpful for me. A lot of this is on intuition, so if we look at all of these different problems, I'll let you read the examples. There's 3 of them there. But we're going to go right to the problems the students have been working on already. For example, the first one, show that in any group of 13 people there will be 12. So I took the number of items, which in this case are people, 13 people over pigeonholes. And that would be 12 months. If you divide that, you're going to have 1 person per month with leftover. So there's going to be at least 1 month with 2 or more. Well, it's actually with 2 people. Isn't necessarily 3 or more. Okay. Is that part okay? And this is by pigeonhole principle. Let's try this number 2. 7 darts are thrown into a circular dart board of radius 10. Okay? Assuming that all the darts land on the dartboard, show that there are 2 darts which are 10 centimeters apart. So the idea here is that you want to take these 7 darts and evenly distribute them as best you can, and their distance will be 10 centimeters apart. So where did you put the 6 of them? On the edge, right? 1, 2, 3, 4, 5, 6. These are all evenly distributed, but how far apart are they? Now, you're saying 10 because if you went to the center and you added the 7th dart, are these 7 darts as totally distributed as you could get? Yep. The 6 are distributed to the center. Now, each of these distances to the radius are 10. What's the distance from dart 1 to dart 2? What's this short distance? Well, you get 10 because there's 360 degrees in a whole circle, and you divide by 1, 2, 3, 4, 5, 6 triangles. That's going to be 60 degrees. Now, if this is 60 and they're isosceles, all of these angles are 60, so that means outside here, each of these will be 10. So if we completely distribute these, 6 around the outside, 10 centimeters apart, and 1 in the center, 10 centimeters from each one, you can say that 2 darts are at most 10 centimeters apart by pigeonhole principle. So again, evenly distributed, mathematically distributed, and look for remainders. 10 children attend a party and each one receives at least one, so that's important, of a total of 50 prizes. Show that there were at least 2 children that received the same number of prizes. Did anybody make any headway on this one? What, Alex?
Just do 1 plus 2 all the way up.
Yeah, because if each kid has a different total, 1 plus 2 plus 3 all the way to 10. Let's add these up. And what is that? Did we talk about the shortcut for this?
11.
You go, these 2 is 11, these 2 is 11, these 2 is 11, 2 is 11, these 2 is 11, and that gives you 5 11s, which is 55, right? So now, here's the hard part. How do you write this?
Like that.
Well, what you probably would want to do is you probably would want to say, okay, since there are 50 prizes and a total of 55 needed to give each child a different number of prizes. "55" is greater than 50, therefore some children receive same total of prizes by pigeonhole principle. Write it as best you can. Here's the thought. This is 55. We don't have 55, so take this 10. What could this 10 be in order to get this total of 50? 5, but then it's going to be a duplicate, isn't it? And so you could do that by changing these. You know, this could be a 6, and this could be an 8. Well, you already have 8 and 6. So no matter how you do it, it's going to be, some of the kids are going to have. All right? What if there were 57 prizes total?
We don't have to worry.
Yeah, because one of them could have 12. Good. I'll let you try some of these. Let's do this easy one here. Number 6, what's the minimum number of people needed to ensure that at least 2 of them have the same birthday? How many would you need? 366 days in a year. And how many people, if we distributed them, one for each day with leap year, then we'd need how many? 367 people, sure. Then you'd be insured. Oh, assured. There are 8 black socks, 14 white socks. Calculate the minimum number of socks needed from the drawer. I've heard it said if you reach into a drawer in the dark, you pull out a sock. Let's say it's a black sock. What will the next one be? White. If you drew a black, it would be a match. But let's say it's a white. And then the third one is either a black or a white. No matter what, you're going to have a match. Does it matter how many you have? No. 3 socks. Now this one's interesting. You have 14 white and 8 black. How many would you need? 2 different colored socks are drawn. What's the minimum number to get 2 of the same color? Have a good evening. Well, why'd you say 15? Why not 9? What's wrong with 9? But there's 8 black socks. If I drew 9, I'd be set. But they could be 9 white. So to be totally sure, what would it be? 15, yep. You get the idea how this works? And then these are fine. Those are good. Would you look at circle number 15? I'm not really sure about the explanation on that one. If you can come up with that and explain it to me, I would love it. The rest go pretty well for me, but that one, I'm not so sure. Okay. If you go to review set A, the very first slide is a list of what's on the test on Friday. You can start getting a little jump start on that. Prime numbers, congruences, Chinese remainder theorem. This I can guarantee you for sure you're going to have. So those you can start. Well, these two pretty much do, but these I know for sure are going to be on there. Make sure you study those. And I thought I had this one. Prime numbers are just used all the time. But for tomorrow, I want you to do problems 1, 2, 3, 4, and 5. Super, super helpful review. Get started on those, do 1 through 5, and I am going to check your 1 through 5 tomorrow. Not the pigeonhole.